Welcome to this lecture on Principal Component Analysis, or PCA. PCA is a foundational technique in statistics and machine learning for reducing the dimensionality of datasets, extracting important features, and visualizing complex data. Developed by Carl Pearson in 1901, PCA is widely used in exploratory data analysis as a pre-processing step for predictive modeling and for uncovering hidden patterns in high-dimensional data. In this notebook, we will cover a range of topics to give you a complete understanding of PCA. We'll start with an introduction, then dive into the mathematical foundations. We'll discuss the practical motivations for using PCA and the necessary data preparation steps. We'll apply PCA to a real-world data set, visualize the results, and learn how to choose the right number of components. We'll also explore how to reconstruct data from the components and quantify information loss. Finally, we'll look at the limitations and best practices for using PCA. Let's begin with the introduction. PCA is an unsupervised linear transformation technique that projects data onto a lower dimensional space while preserving as much of the original variance as possible. It is widely used for several purposes, including reducing the number of features, visualizing high-dimensional data, removing multicollinearity between features, noise reduction, and as a pre-processing step for other machine learning algorithms. The main motivation is that high-dimensional data can be very difficult to interpret and visualize. Many features may be correlated or redundant, and reducing the dimensionality can often improve a model's performance and its ability to generalize. PCA has many real-world applications, such as in image compression, genomics, and financial analysis. Now for the mathematical foundations. Given a data set, PCA finds a new set of orthogonal vectors called principal components. The first principal component is the direction in the data that maximizes the variance. Each subsequent component maximizes the remaining variance while being orthogonal or at a right angle to all the previous components. The process involves a few key steps. First, we center the data by subtracting the mean from each feature. Second, we compute the covariance matrix of the centered data. Third, we perform an eigendecomposition on this covariance matrix to find its eigenvalues and eigenvectors. The eigenvectors corresponding to the largest eigenvalues are our principal components. Geometrically, you can think of each principal component as defining a new axis in the feature space. The first component points in the direction of the most spread in the data, and the subsequent components capture the next highest directions of spread, all while being uncorrelated with each other. The amount of variance that each principal component captures is given by its corresponding eigenvalue. We can calculate the explained variance ratio for each component, which tells us the proportion of the total information that component holds. So, why do we use PCA? There are several practical motivations. It helps us deal with the curse of dimensionality, where having too many features makes analysis difficult. It can reduce noise by filtering out the components with low variance. It's a powerful tool for visualization, allowing us to plot high-dimensional data in 2 or 3 dimensions. Because the principal components are uncorrelated, it can improve the performance of some machine learning algorithms that are sensitive to multicollinearity. However, PCA is not always the right tool. You shouldn't use it when the interpretability of the original features is crucial, because the new components are combinations of the old ones and can be hard to interpret. Also, if the relationships in your data are highly nonlinear, you might want to consider alternatives like kernel PCA or TSNE, which is pronounced TSNE. Proper data preparation is essential before applying PCA, as the technique is sensitive to the scale of the data. First, all features should be standardized to have a mean of 0 and a standard deviation of 1. This ensures that all features contribute equally. Second, PCA cannot handle missing values, so you must either impute them or remove the corresponding samples. Third, since PCA requires numeric input, categorical variables must be converted using a method like one-hot encoding. And finally, outliers can heavily influence the principal components, so it's a good practice to detect and handle them beforehand. Let's demonstrate these preparation steps with the telecom churn dataset. In the Python code, we first load the data. We then separate the numeric and categorical columns. We use a simple imputer to fill any missing numeric values with the mean of their respective columns. For the categorical columns, we use a one-hot encoder. We then combine the processed numeric and encoded categorical features. The most crucial step is last. We use the standard scaler to standardize all features. The code finishes by plotting a heat map of the correlation matrix for a subset of the features, which visually confirms that there are correlations in the data that PCA can help simplify. Now, let's apply PCA to this preprocessed dataset. We'll use the PCA class from scikit-learn. After fitting PCA to our scaled data, we can examine the explained variance. The first plot shows the cumulative explained variance. This plot helps us see how much of the total information is retained as we add more principal components. You can see that with just a few components, we can capture a large portion of the variance. The second plot is a scree plot, which is a bar chart of the variance explained by each individual component. This scree plot is useful for finding the elbow point, which suggests a good cutoff for the number of components to keep. In practice, a common approach is to choose the smallest number of components that explain a certain percentage of the variance, for example, 90%. One of the most powerful uses of PCA is for visualization. Let's project our high-dimensional data onto the first two principal components and see what it looks like. We'll also color the data points by the customer's churn status. In the code, we create a new PCA object, this time specifying that we only want two components. We then transform our scaled data into this new 2D space. The resulting scatter plot shows the data projected onto the first and second principal components. By coloring the points by churn, we can see if the two classes, churn yes and no, are separated in this new reduced space. This can reveal patterns that were not visible in the original data. Choosing the right number of components is a key decision. As we've seen, we can use the cumulative explained variance plot to select enough components to meet a certain threshold, like 90%. The scree plot's elbow is another heuristic. Other methods include the Kaiser criterion, which suggests keeping components with eigenvalues greater than 1, and parallel analysis, which compares the eigenvalues of your data to those from random data. Remember, using fewer components means more data compression, but also greater information loss. PCA is a reversible transformation. This means we can reconstruct the original data from a smaller number of principal components. The difference between the original data and the reconstructed data represents the information loss. In the code, we demonstrate this by using the first 10 components to reconstruct the data. We use the inverse transform method to project the data back into the original feature space. We then calculate the mean squared reconstruction error. The plot shows the feature values for a single sample comparing the original values to the reconstructed ones. You can see they are very similar, which indicates that the first 10 components captured most of the important information. We can also use PCA to create 3D visualizations. The process is the same as for the 2D plot, but this time we specify that we want to keep 3 components. The code then generates an interactive 3D scatter plot, again colored by churn status, which can give us another perspective on the structure of our data. Finally, it's important to be aware of the limitations and best practices of PCA. The biggest limitation is that PCA only captures linear relationships. For nonlinear data, you should consider other methods. Always standardize your features before applying PCA. While PCA is great for dimensionality reduction, the principal components themselves can be difficult to interpret. And remember that high explained variance doesn't always guarantee better performance in a downstream machine learning task. In summary, PCA is a fundamental tool for dimensionality reduction, visualization, and noise reduction. It is most effective when used thoughtfully, with careful attention to data preparation, interpretability, and the linear nature of the technique. This concludes our lecture on principal component analysis. Thank you.